Today I want to look at the Poisson approximation to the binomial distribution. Let's first look at one binomial distribution that we shouldn't find too difficult. Suppose x is twiddle binomial 50.05. I want to find the probability that x equals 2. I can use the cumulative tables because I'm lazy. Probability x less than or equal to 2, subtract less than or equal to 1, and we get 0.2611. We'll come back to that. The expected mean is NP, is 50 times 0.05, which is 2.5. What I want to do now is look at the Poisson distribution with the same mean, 2.5. If we do this, we will find the probability that y is 2 is the probability that y is less than or equal to 2 minus less than or equal to 1 using cumulative tables again. And that gives us 0.2565. So for the binomial, we got the probability that x was 2 was 0.2611. And for the Poisson, we got the probability that y was 2 is 0.2565. And these two values are very nearly equal. Well, let's look at that in a little bit more detail. Well, first of all, to look at the binomial distribution that we had just now, 50.05. Let me explain what this graph is about. It's a histogram showing this distribution. Here is x equals 2. The probability for x equals 2 was 0.2611, which means that the area of this bar from 1.5 to 2.5 will be 0.2611. The same is true for all the other red bars that you can see. So because the width of each bar is 1, the height is actually the probability in each case. So this is a picture of what happens with binomial 50, 0.05. It only goes as far as 8. Once you get beyond 8, the probabilities are so small that you can't see them. It doesn't mean they aren't there. It does go all the way up to 50, but very, very small and insignificant. I've put here exactly the same idea, a histogram for the Poisson distribution with a mean of 2.5. There we have 0.2565 is the area of that bar at 2 because the width at the bottom is 1. And you can see how very, very, very similar these are. Not quite the same. There's just a slight difference between that one, and there's a bigger difference there, but very similar. Both dying out round about the 8. That's gone right down. That's got just a tiny little bit left. So that the Poisson distribution with a mean of 2.5 would be a good approximation for the binomial distribution with n is 50 and p is 0.05. Does this mean that the Poisson distribution is always going to be a good approximation for the binomial? The answer is no. Here I have a binomial distribution 15.25, expected mean 3.75, and here is the corresponding Poisson distribution with a mean of 3.75. Well, firstly, just look at the shape. 2 exactly the same. No, we step down. That one's significantly higher than that one. There's sort of similarities in the shape, but this isn't that good an approximation. And if we look at the numbers, the top of this bar at 3 is 0.2067, and the top of the bar at 3 is 0.2262. Not so good as we had before. So in this case, we haven't got such a good agreement. We had 15 and 0.25. Didn't work as well. What happens if we take 10 and 0.3? The expected mean here, 10 times 0.3 is 3. There's the corresponding Poisson distribution. And once again, although there's a sort of similarity in the shape, we really don't want to take these being approximately the same. Probability of 2 is bigger than the probability of 4. Probability of 2 is less than the probability of 4. I mean, there are significant differences in shape in what's going on between those two. The height here is 0.2668, 0.2420. So, yes, very, very approximate. I don't like it. Let's look at this one. This is looking better. Shape's better. 2700, 2794, 30.07, mean 2.1, mean 2.1. Yes, when we started, we had a value of p which was 0.05, and we had a good agreement. Now I've got a value of p which is 0.07, and we've got a good agreement again. Well, let's go on, see what else happens. It looks as if the binomial and the Poisson agree quite well when p is small. But, and there's always a but. Let's look at this one. If we take x1 is binomial 30.96, then very definitely p is not small. P is in fact close to 1. And this is one which you won't find mentioned very often. It's not mentioned in your textbook. A lot of people ignore it. And then they set a question on this in the exam and you fall down a great big hole. What we need to do is to look at x2, which is what I would sort of describe as the opposite of x1. So if the probability of success with x1 is 0.96, the probability of success with x2 will be 0.04, and x2 will be 30 minus x1. So if there are 4 successes with x1, there will be 26 values of x2. It's like red flowers and yellow flowers. If I've got 4 red flowers, I will have 26 yellow flowers. Probability of red, 0.96. Probability of yellow, 0.04. That's what I mean by the opposite. Now, I do have a value of p which is small. But I've started with one which is close to 1. And that's what you must be looking out for. If the value of p is close to 1, a little bit of adjustment, and you can use a Poisson approximation. Well, let's see how well it does agree. 30.04. So there is 30.04. Here is the histogram, 0, 1, 2, 3. Poisson 1.2, 0, 1, 2, 3, etc. And the top value is 0.3673. The top value is 0.3614. Shape, pretty good. So yes, Poisson is a good approximation when p is small, but don't ignore what happens when p is close to 1. So that's all summarized here. Binomial NP, Poisson, good approximation with lambda is NP, n is large. What does that mean? Well, it depends to a certain extent how small p is. If p is very small, then perhaps n being 20 would be good enough. If p isn't very small, perhaps you might need to go for n is 50. What does small mean? Well, we usually take round about less than 0.2 as being small. I still wouldn't really think 0.15 was all that small, and the smaller the better. So if you take a really small number, 0.01, then you will get a good approximation if you've got n is, say, 30 or 40. And here, of course, is the but. If 1 minus p is small, in other words, p is near 1, we use x2 is n minus x1. x2 then has n, and the probability is small and can be approximated by a Poisson. Don't forget this one. Go charging into a problem which wants this, and forget about it, and you've suddenly lost all of the marks.